Dear students, a very warm welcome to MOOCs, massive open online courses on SWAYAM and chemistry. I am Charu Maini from DAV Public School, Sector 49, Gurugram. In this session, I will be presenting the second module on the chapter General Principles and Processes of Isolation of Elements. After going through this module, you will be able to apply the concept of thermodynamics in metallurgical processes, appreciate coupling of reactions to make non-feasible reactions as feasible, evaluate the use of carbon monoxide and coke as a favorable reducing agent at a given temperature. You will be able to explain why specific reducing agents are used for the reduction purposes and apply the knowledge of electrochemistry and redox reactions to extraction of elements. In the previous module of this chapter, you studied about the first two steps in metallurgy of metals, that is concentration of ore and conversion of metal compound into metal oxide. Now, in this module, we will discuss how to reduce the metal oxide to metal. In class 11, you learned the concept of feasibility of a reaction on the basis of free energy. Recall that only those reactions which have a negative value of Gibbs free energy are feasible. The basic concept of thermodynamics helps us in understanding the theory of metallurgical transformations. You must be able to recall that the change in Gibbs energy delta G for any process at any specific temperature is described by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy change and delta S is the entropy change for the process. For any reaction, this change could also be explained through the equation delta G naught is equal to minus RT natural log K, where K is the equilibrium constant of the reactant product system at the temperature T. A negative value of delta G implies a positive equilibrium constant K in the equation 2, and this can happen only when the reaction proceeds towards the products in the forward direction. From these facts, we can make the following conclusions. When the value of delta G is negative in equation 1, only then the reaction will proceed. If delta S is positive on increasing the temperature T, the value of T delta S would increase such that delta H is less than T delta S, and hence delta G will become negative as delta G is equal to delta H minus T delta S. A very interesting concept is coupling of reactions. If reactants and products of two reactions are put together in a system and the net delta G of the two possible reactions is negative, the overall reaction will occur even if individually the reaction is not feasible. The concept of coupling of reactions involves process of interpretation of free energy values of the coupled reaction, getting the sum of their delta G and analyzing the magnitude and sign. Such coupling is easily understood through Gibbs energy delta G naught versus T plots for the formation of the oxides as shown in figure 1. The plots are called Ellingham diagrams. These graphical representations of Gibbs energy were first used by H. J. T. Ellingham. Let us first understand the use of Ellingham diagrams. These are graphs which provide a sound basis for considering the choice of reducing agent in the reduction of oxides. This is known as Ellingham diagram. Such diagrams help us in predicting the feasibility of thermal reduction of an ore. The criterion of feasibility is that at a given temperature, Gibbs energy of the reaction must be negative. Ellingham diagrams normally consist of plots of delta G naught versus T for formation of oxides of elements. For the reaction, metal atoms react with oxygen to form metal oxide. In this reaction, the gaseous amount, hence molecular randomness, is decreasing from left to right due to the consumption of gases, leading to a negative value of delta S, which changes the sign of the second term in the equation 1. Subsequently, delta G shifts towards higher side despite rising temperature. The result is positive slope in the curve for most of the reactions shown above for formation of metal oxide. Each plot is a straight line except when some change in the phase, that is from solid to liquid or liquid to gas, takes place. The temperature at which change occurs is indicated by an increase in the slope on positive side. Example, you can see in the zinc oxide plot, the melting is indicated by an abrupt change in the curve. There is a point in a curve below which delta G is negative, so metal oxide is stable. Above this point, metal oxide will decompose on its own. In an Ellingham diagram, the plots of delta G naught for oxidation and therefore reduction of the corresponding species of common metals and some reducing agents are given. The value of delta G naught, etc. for formation of the oxides at different temperatures are depicted, which make the interpretation easy. Similar diagrams are also constructed for sulfides and halides, and it becomes clear why reduction of metal sulfide is difficult. There, the delta G naught formation of metal sulfide is not compensated. The reducing agent gets oxidized to its oxide, and in turn the metal oxide is reduced. The role of reducing agent is to provide a delta G naught negative and large enough to make the sum of delta G naught of the two reactions, oxidation of the reducing agent and reduction of the metal oxide, as negative. As we know, during reduction, the oxide of a metal decomposes as metal oxide to metal in solid or liquid state, plus oxygen gas is released. Delta G naught for reaction 3 is positive, as this is a highly endothermic process. The reducing agent takes away the oxygen. The equation 3 can be visualized as reverse of the oxidation of the metal, and then the delta G naught formation value is written in the usual way as metal in solid or liquid state plus oxygen gas, giving us metal oxide. If reduction is being carried out through equation 3, the oxidation of the reducing agent, that is for example carbon or carbon monoxide, will be there. For example, as carbon solid reacts with oxygen gaseous to give carbon monoxide, or carbon monoxide reacts with oxygen to give carbon dioxide. If carbon is taken, there may also be complete oxidation of the element to carbon dioxide. As in the reaction, carbon reacts with oxygen gaseous to give carbon dioxide. On subtracting the equation 4, that it means adding the negative or the reverse form as in equation 3 from one of the three equations 5, 6 or 7, we get respectively the following reactions as the reaction number 8, 9 or 10. Metal oxide plus carbon gives metal in the solid or liquid state plus carbon monoxide. Metal oxide plus carbon monoxide gives metal plus carbon dioxide, or metal oxide plus carbon gives metal in solid or liquid state plus carbon dioxide. These reactions describe the actual reduction of the metal oxide that we want to accomplish. The delta G naught formation value for these reactions in general can be obtained by similar subtraction of the corresponding delta G naught formation values. As we have seen, heating, that is increase of temperature for a reaction with positive entropy change, positive delta S, favors a negative value of delta G naught formation. Therefore, the temperature is chosen in such a manner that the sum of delta G naught formation in the two combined redox processes is negative. In delta G naught formation versus T plots, this is indicated by the point of intersection of the two curves. As you can see in the graph, curve for metal oxide and that for the oxidation of the reducing substance. After that point, the delta G naught formation value becomes more negative for the combined process, including the reduction of metal oxide. The difference in the two delta G naught formation values after that point determines whether reduction of the oxide of the upper line is feasible by the element represented by the lower line. If the difference is large, the reduction is easier. Let us see the limitations of Ellingham diagram. The graph simply indicates whether a reaction is possible or not. That is, the tendency of the reduction of a reducing agent is indicated. This is so because it is based only on the thermodynamic concepts. It does not say anything about the kinetics of the reduction process. We cannot answer questions like how fast it could be. The interpretation of delta G naught is based on the equilibrium constant K. Thus, it is presumed that the reactants and the products are in equilibrium. For example, metal oxide plus a reducing agent A are in equilibrium with metal plus oxide of A. This is not always true because the reactant or product may be solid. However, it explains how the reactions are sluggish when every species is in solid state and smooth when the ore melts down. It is interesting to note here that delta H, that is the enthalpy change, and delta S, that is the entropy change values for any chemical reaction remain nearly constant even on varying temperature. So, the only dominant variable in the equation 1 becomes temperature. However, delta S, that is the change in entropy, depends much on the physical state of the compound. Since entropy depends on disorder or randomness in the system, it will increase if a compound melts, that is from solid to liquid, or vaporizes from liquid to gaseous state. Since molecular randomness increases on changing the phase from solid to liquid and from liquid to gas. Let us see the applications of thermodynamics and Ellingham diagrams in extraction of some metals. Extraction of iron from its oxides. Oxide ores of iron, after concentration through calcination or roasting, are mixed with limestone and coke and fed into a blast furnace from its top. Here, the oxide is reduced to the metal. Thermodynamics helps us to understand how coke reduces the oxide and why only this furnace is chosen. One of the main reduction steps in this process is iron oxide reacting with coke to form iron plus carbon monoxide. It can be seen as a couple of two simpler reactions. In one, the reduction of iron oxide is taking place, and in the other, coke is being oxidized to carbon monoxide. Iron oxide decomposes to give iron and oxygen, and coke reacts with oxygen to give carbon monoxide. When both the reactions take place to yield the equation number 10, the net Gibbs energy change becomes delta G carbon to carbon monoxide plus delta G iron oxide to iron, giving us delta G formation. And naturally, the resultant reaction will take place when the right hand side of the equation number 14 is negative. The delta G naught versus temperature plot representing reaction number 12, the plot goes upwards and the representing the change carbon to carbon monoxide goes downwards at the temperature above 1073 Kelvin approximately. The coke carbon monoxide line becomes below the iron oxide line, which is less than the delta G for iron oxide. So, in this range, coke will be the reducing agent for iron oxide and will itself be oxidized to carbon monoxide. In a similar way, the reduction of Fe3O4 and Fe2O3 at relatively lower temperatures by carbon monoxide can be explained on the basis of the lower lying points of intersection of their curves with carbon monoxide, carbon dioxide curve in the figure number 1. In the blast furnace, the reduction of iron oxide takes place in different temperature ranges. Hot air is blown from the bottom of the furnace and the coke is burnt to give temperatures up to 2200 kelvins in the lower portion itself. The burning of coke therefore supplies most of the heat required in the process. The carbon monoxide and heat move to the upper part of the furnace. In the upper part, the temperature is lower and the iron oxides Fe2O3 and Fe3O4 coming from the top are reduced in steps to iron oxide FeO. Thus, the reduction reactions taking place in the lower temperature range and in the higher temperature range depends on the point of corresponding intersections in the delta G naught versus temperature plots. These reactions can be summarized as follows. At a range of temperature 500 to 800 kelvins, that is at the top of the blast furnace, we have iron oxide Fe2O3 plus carbon monoxide giving us Fe3O4 plus carbon dioxide, or Fe3O4 reacting with carbon monoxide to form iron and carbon dioxide. Fe2O3 also reacts with carbon monoxide to give FeO plus carbon dioxide. At 900 to 1500 kelvins, that is at high temperature in the blast furnace, coke reacts with carbon dioxide to form carbon monoxide. Also, iron oxide reacts with this carbon monoxide formed to form iron and give carbon dioxide. Limestone is also decomposed to calcium oxide, which removes silicate impurity of the ore as slag. The slag is in the molten state and separates out from the iron, as you can see at the bottom of the blast furnace. The iron obtained from the blast furnace contains about 4% carbon and many impurities in the smaller amounts, example sulfur, phosphorus, silicon and manganese. This iron is known as pig iron and cast into variety of shapes. Cast iron is different from pig iron and is made by melting pig iron with scrap iron and coke using hot air blast. It has slightly lower carbon content, about 3%, and is extremely hard and brittle. Further reductions form wrought iron or malleable iron, which is the purest form of commercial iron and is prepared from cast iron by oxidizing impurities in a reverberatory furnace lined with hematite. This hematite oxidizes carbon to form carbon monoxide, Fe2O3 plus coke giving us iron plus carbon monoxide. Limestone is added as a flux and sulfur, silicon and phosphorus are oxidized and passed into the slag. The metal is removed and freed from the slag by passing through rollers. Now, let us understand the extraction of copper from cuprous oxide using the Ellingham diagrams. In the graph of delta G naught versus temperature for the formation of oxides, the cuprous oxide line is almost at the top. So, it is quite easy to reduce oxide ore of copper directly to the metal by heating with coke. Both the lines of coke, carbon monoxide and coke and carbon dioxide are at much lower positions in the graph, particularly after 500 to 600 kelvins, as you can see in the graph. However, most of the ores are sulphide and some may also contain iron. The sulphide ores are roasted, smelted to give oxides, as in the reaction cuprous sulphide reacts with oxygen to give cuprous oxide plus sulfur dioxide. The oxide can then be easily reduced to metallic copper using coke. Cuprous oxide plus coke gives copper plus carbon monoxide. In actual process, the ore is heated in a reverberatory furnace after mixing with silica. In the furnace, iron oxide slags off as iron silicate and copper is produced in the form of copper matte. This contains copper sulphide and iron sulphide. As in the reaction, iron oxide plus silica gives iron silicate. Copper matte is then charged into silica lined converter. Some silica is also added and hot air blast is blown to convert the remaining iron sulphide, iron oxide and copper sulphide to copper oxide to the metallic copper. Following reactions take place in the furnace. Iron sulphide plus oxygen giving iron oxide and sulphur dioxide, iron oxide plus silica giving iron silicate, copper sulphide plus oxygen giving cuprous oxide and sulphur dioxide, cuprous oxide plus cuprous sulphide giving copper and sulphur dioxide. The solidified copper obtained has blister-like appearances due to the evolution of sulphur dioxide as we saw in the reaction, and so it is called a blister copper. Now, let us understand the extraction of zinc from zinc oxide. The reduction of zinc oxide is done using coke. The temperature in this case is higher than that in the case of copper. For the purpose of heating, the oxide is made into briquettes with coke and clay. Zinc oxide reacts with coke at 673 Kelvin to form zinc and carbon monoxide. The metal is distilled off and collected by rapid chilling. So, these were the pyrometallurgical methods of obtaining metal from their oxides. Now, let us understand some electrochemical principles of metallurgy as applied to metals of high reactivity. We have seen how principles of thermodynamics are applied to pyrometallurgy. Similar principles are effective in the reductions of metal ions in solutions or molten state. Here they are reduced by electrolysis or by adding some reducing element. In the reduction of a molten metal salt, electrolysis is done. Such methods are based on electrochemical principles which could be understood through the equation delta G naught is equal to minus N E naught F. Here N is the number of electrons and E naught is the electrode potential of the redox couple formed in the system. More reactive metals have large negative values of the electrode potential, so their reduction is difficult. If the difference of two E naught values corresponds to a positive E naught and consequently a negative delta G naught in equation number 29, then the less reactive metal will come out of the solution and the more reactive metal will go into the solution. For example, copper ions react with iron to form copper and iron ions. Now, let us understand the metallurgy of aluminium. In the metallurgy of aluminium, purified alumina is mixed with Na3AlF6 or CaF2, which lowers the melting point of the mix and brings conductivity. The fused mixture is electrolyzed, steel cathode and graphite anode are used. The graphite anode is useful here for reduction to the metal. The overall reaction may be taken as alumina plus coke giving aluminium plus carbon dioxide. This process of electrolysis is widely known as Hall-Héroult process. The electrolysis of the molten mass is carried out in an electrolytic cell using carbon electrodes. The oxygen liberated at anode reacts with the carbon of the anode producing carbon monoxide and carbon dioxide. This way, for each kilogram of aluminium produced, about 0.5 kilograms of carbon anode is burnt away. The electrolytic reactions are at cathode, aluminium 3 plus ions which are there in the melt combined with 3 electrons to give aluminium metal. At anode, coke reacts with oxide from the melt to form carbon monoxide and releases 2 electrons. The coke plus oxide ions give also carbon dioxide and 4 electrons. Now, let us understand another method, that is hydrometallurgy. Copper from low grade ores of copper and scrap copper is extracted by hydrometallurgy. It is leached out using acid or bacteria. The solution containing copper ions is treated with scrap iron or hydrogen. As seen in the equation, copper plus hydrogen gives copper plus hydrogen ions. Let us understand oxidation and reduction to get elements. For example, extraction of chlorine. Besides reductions, some extractions are based on oxidation, particularly for nonmetals. A very common example of extraction based on oxidation is the extraction of chlorine from brine, that is sodium chloride from seawater, which is an abundant source of sodium and chlorine in the form of common salt. As in the reaction, chloride ions reacts with water to form hydroxide ions and hydrogen plus releases chlorine gas. The delta G naught for this reaction is positive, that is positive 422 kilojoules. Using delta G naught is equal to minus NFE naught, we get E naught is equal to minus 2.2 volts. Naturally, it will require an external electromotive force, that is greater than 2.2 volts during electrolysis. Thus, chlorine is obtained at the anode as chloride ions, which is oxidized, and byproducts of this electrolysis process are hydrogen at the cathode and aqueous sodium hydroxide. Extraction of sodium and chlorine. In case electrolysis of molten NaCl is carried out, sodium metal is produced at the cathode as reduction product of sodium ions, and chlorine gas is obtained at the anode as the oxidation product of chloride. Sodium hydroxide and hydrogen is not produced in this case as expected. Following reactions take place in case of electrolysis of molten sodium chloride. At cathode, sodium ions from the melt combine with electron to form sodium metal, that is reduction, and at anode, chloride ions from the melt release electrons and form chlorine gas, which is oxidation. Now let us understand extraction of gold and silver. As studied earlier, extraction of gold and silver involves leaching the metal with cyanide. This is also an oxidation reaction, as silver gets oxidized to silver ions or gold gets oxidized to gold ions. The metal is later recovered by displacement method, which is a reduction process. In this reaction, zinc acts as a reducing agent. The reaction is gold combines with cyanide and water in presence of oxygen to form a complex of gold cyanide plus hydroxide ions. The gold cyanide complex reacts with zinc to form gold and tetracyanozincate. Thus, in the same manner, silver is also obtained. So, now let us summarize what we have studied today. The metal compounds, example oxides, sulfides, are reduced to the metal. The reducing agents used are carbon, that is coke, or carbon monoxide, or even some metals. In these reduction processes, the thermodynamics and electrochemical concepts are given due consideration. The metal oxide reacts with a reducing agent, the oxide is reduced to the metal, and the reducing agent is oxidized. In the two reactions, the net Gibbs energy change is negative, which becomes more negative on raising the temperature. Conversion of the physical states from solid to liquid or liquid to gas and formation of gaseous states favors the decrease in Gibbs energy for the entire system. This concept is graphically displayed in the plots of G naught versus temperature, that is Ellingham diagrams, for such oxidation or reduction reactions at different temperatures. The concept of electrode potential is useful in the isolation of metals, example aluminium, silver, gold, where the sum of the two redox couples is positive, so that the Gibbs energy change is negative. Extraction of iron is done by reduction of its oxide ore in the blast furnace. and copper is extracted by smelting and heating in a reverberatory furnace. Extraction of zinc from zinc oxide is done using coke. Extraction of aluminium is usually carried out from its bauxite ore. The molten purified alumina is mixed with cryolite as a flux and then electrolyzed to obtain pure aluminium at the cathode. Extraction of sodium is carried out from molten sodium chloride. The molten NaCl is electrolyzed to obtain pure sodium at the cathode and chlorine gas is obtained at the anode. Electrolysis of brine, that is, aqueous NaCl produces chlorine at the anode, but the byproducts are hydrogen gas at the cathode and aqueous solution of sodium hydroxide in the cell. Extraction of gold and silver involves leaching and the metal with cyanide and then using zinc as a reducing agent to recover the pure metals. A summary of the occurrence and extraction of some metals is presented in the table. Hope you have understood today's module. Thank you.